All right, we're finally in a new chapter. We're hitting the praise hands emoji, sorry. I would also like to announce that I was successful. We got a new mic, so hopefully no popping sounds. Shouldn't be any popping sounds. I'm announcing it at the start of the lecture on the recording so that if you want to, you can listen to my voice, and there shouldn't be any popping sounds. If there are, send me a strongly worded letter. Okay, gases. You may know that suction cups, if you put a suction cup or anything else with a suction cup type thing onto a piece of glass or any other surface that's really flat, it'll just stick and stay there, but it's not sticky. Like if you try to press it to your hand, it doesn't stay there. Why and how? How does it stay there if it's not sticky?
The surrounding air pressure is pushing on it.
Yeah, it's air pressure. So the way that suction cups work is that you basically are pushing out as much gas as possible from one side, nice crack. And on the other side is all of the gas, all of the atmospheric pressure from the gas, all these particles constantly hitting it from one side. And because there's nothing hitting it from the other side, the suction cup gets pushed into the flat surface and held there. If you had a 2-inch diameter suction cup, it would be pushed on by a force of about 46 pounds of force. So it's about 50 pounds of pressure holding that suction cup against the wall, which is why suction cups can be so hard to remove. If you lift up the edge of a suction cup or something else with a suction cup on it, that lets in air and that equalizes the pressure, so the gas will flow in around the sides. If you lift the edge up, the gas flows in and starts colliding with the other side, and now the pressure is the same on both sides, and it comes off super easily. This is also why suction cups don't really work if I'm thinking of like in the bathroom, because we've got one of the ones that hangs on the shower head, but it's also got suction cups that are supposed to hold it to the wall. It doesn't work if you have rough tile. The suction cups just do nothing. If you've got nice smooth flat tile, or if you've got glass or some other flat surface, then it will actually hold, but anything with rough edges lets air get in under the edges, and so the suction cup's not going to work. Or if you just have a dirty window or other surface that you're putting it on. For gases, we are going to use the kinetic molecular theory to model gases. This is a simplified model. So it's not exactly the same way that gases work in the real world, but it lets us predict correct behavior for many gases under many conditions. It's not perfect, and it will break down under some conditions. We're going to focus on where it works well, and there's 5 points. We've got them all on one slide for you. We're also going to talk about them more individually as we get on. So gas, any gas, like the air that we're breathing right now, consists of tiny particles of matter. They have mass, they take up space, and they are in constant motion. All gas is in constant motion. These gas particles can collide with each other. The collisions are elastic. They bounce perfectly. So like the best bouncy ball that you've ever had in your life, you drop it from a height and it comes up and it's almost right back at your fingertips, probably a little less. But in our model of gases, if you drop the bouncy ball, it hits the ground and it comes exactly up to your hands again. So you just, as many times as you want to, you just leave it bouncing for 50 hours, you come back, same height, grab your bouncy ball, and then go bounce it somewhere else, presumably. So there's no energy loss, there's no friction, there's none of that. And the gas particles are also separated by large distances relative to their size. So there's lots of empty space between the gas particles. They're not all crammed together. It's not like they're almost a liquid. There's lots and lots of empty space in between the gases, the gas particles. The gas particles additionally don't attract or repel each other. They're not sticky nor repulsive. So if you think of magnets, when magnets get close to each other, they either repel each other or attract each other. In the real world, lots of particles do that to a very small extent. Our gas particles in our kinetic molecular theory don't do any of that. They're more like billiards balls, pool balls. They hit and they bounce off. They don't stick to each other, none of that sort of stuff. The speed of the particles, how fast the particles are moving, depends at least in part on temperature. Speed depends on temperature. High temperature equals fast. What would low temperature mean? Slow. So cold is slow, hot is fast. Completely unrelated to anything in the class, but my brain thought of it. Are lemons fast or slow? Lemons are fast. Thank you. Kinetic molecular theory is consistent with the properties of gases. So one of the things here, gases are compressible. There's lots of empty space in between them. You can reduce the amount of empty space. Because there's lots of empty space between the gas particles, if you force them into a smaller environment, they will fit up to a certain point. It's sort of similar to students in a class. We could all fit into one of the larger lecture halls on the Visalia campus, and we would probably just spread out a little bit more. We could also probably, if we really needed to, it would be against fire code, but we could probably fit into a much smaller classroom, one of like the computer labs on this floor. It's just that we would all be standing and we would be uncomfortable. The pressure in the room and the temperature in the room would probably turn up a little bit. So gases are compressible because of the empty space. Gases also assume the shape of their container. The gases do not interact with one another, so they're not going to clump together. They're also not going to force each other apart. They're just going to bounce off of each other. The gas particles will spread out to fill their space. Maybe someday I will bring some really odoriferous food and just open a container up here in the front to demonstrate this. As like the smell eventually wafts its way, like kimchi or something, and the smell will just waft its way out through the class to demonstrate this. But we've probably all experienced the gases assume the shape of their container. You're on a road trip. Hopefully we've been on a road trip because it's a life experience. You stop at a Taco Bell, somebody gets a taco, you pull it out, and everyone eventually can smell the taco. Or like on a bus on a school field trip. I'm thinking of other examples, but they're not as pleasant as Taco Bell. Uh-oh, stinky sort of vibes. Gases also have low densities in comparisons with solids and liquids because there's empty space in between them. Empty space between the particles. And so if you were to take a typical can of soda, like a 12-ounce can of soda, like some Diet Coke, and you expanded that out to a gas, you gasified the can of cola, it would take up like 2 bathtubs in terms of the volume that it would spread out to, which is a drastically larger amount of space. So 12-ounce soda could expand up to almost 500 liters. That's like 2 bathtubs. Your bathtub probably doesn't look like this, but it's a free image that I was able to use. So pressure is a prediction of our kinetic molecular theory. Pressure is the result of constant collisions between the particles in a gas and the surfaces around them. Billions of billions, etc., 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 of tiny collisions that all add up, all happen at once. That is what causes pressure. Pressure is very good. The amount of pressure that we have, that we're adapted to, is very good. It lets us drink from straws. If there's no pressure, you can't drink from a straw, which would be unfortunate. We can inflate basketballs because of pressure. If there's no gas, no basketball. We can also move air into and out of our lungs. We actually just move air out of our lungs, and the atmosphere moves air into our lungs for us, if I'm remembering correctly. Variation in pressure in our atmosphere, also creates wind. It's not caused by trees sneezing, which is a Calvin and Hobbes reference. And changes in pressure also are how we help predict the weather. So wouldn't you like to know weatherman uses the pressure gradients around the planet from lots of different pressure measuring stations to predict weather, and they're actually really quite good at it. The pressure exerted by a gas sample is force over a unit area. Pressure is force over an area. It depends on a lot of factors, including the number of gas particles, few particles will mean few collisions. Collisions are what make pressure, so few collisions means low pressure. If you increase the number of particles, you increase the number of collisions, and you increase the pressure. This is sort of what we're thinking about. How is pressure going to change? It's based on collisions, is one of the two factors. The number of collisions is not infinity, proportional to the pressure. This is one of the underpinnings of how pressure works. You don't have to necessarily have this memorized, but I think having this conceptual basis will let you be more successful in thinking about what things will affect pressure and how they'll affect pressure. So number of collisions is one of the big things. We have probably, all of us, experienced pressure imbalance in some way. You may know that atmospheric pressure is lower at higher elevations. Denver, famously, the mile-high city, has low pressure. If you've never been to Denver, that's fine. You've maybe been up into our local mountains, world-famous mountains. There's also lower pressure up in the mountains. The further up you go, the lower the pressure gets. And if you go changing your pressure up or down, that higher pressure or lower pressure that you experience, if you're going up into higher elevation, you're going to have high pressure in your ears. That's going to cause your eardrums to bulge outward. And if that happens enough, it hurts. It's very painful. So you yawn, you chew some gum, or you've got the superpower where you can just flex the muscle and open the pressure channels in your ear. Must be nice. And then you relieve the pressure, hopefully. Infants and small children on planes often cry because of that painful pressure imbalance. I flew to Seattle over spring break and brought along a little device that let me measure the pressure on the plane, and it was like 0.77 atmospheres. So you would have to pop your ears like 10 to 20 times between being on the ground and being at cruising altitude. which is kind of annoying. Babies are not going to be able to do that, and they're not going to know why their ears hurt, and so they're just going to cry. And you also can't give infants gum to chew on because the doctors don't want you to relieve their pain. I'm just kidding. It's because they'll die. We haven't talked about pressure units, but they're coming up. The pressure here is about 1 atmosphere, and on the plane it was about 0.77 atmospheres, which is a significant difference. It's sort of the same as if you went up into the mountains in terms of the pressure. So lots of ear popping, but happening over a relatively short period of time. For pressure units, we're going to be doing math again. We took like a 3-week break from doing any real math. We're bringing math back. Our simplest unit of pressure is the atmosphere. The atmosphere is the pressure at sea level at the beach, typically. So if you're around the coast in terms of elevation, then you should be experiencing about 1 atmosphere of pressure. We are at relatively low elevation of like 400 feet or something like that. And so we also experience about 1 atmosphere of pressure. The SI unit of pressure, so like the metric unit of pressure essentially, is the Pascal. And that's defined as 1 Newton per square meter. A Newton is a small unit of force. And a square meter is a relatively large area. 3.3 feet by 3.3 feet square. Small unit of force over a very large area, and because of it being a small unit of force over a big area, the Pascal is a really small unit. There's 101,000 of them in 1 atmosphere. So Pascal's really tiny little baby unit in terms of pressure. We're probably not going to use the Pascal very much. If you take a physics class, you'll probably use Pascals if you're doing any pressure stuff. We have a bunch of other pressure units. The millimeter of mercury is one of the original units of pressure. And I like to talk about this one, so we're going to yap about it for a little bit. The way that this works, you take a really long glass tube, really long skinny glass tube, and you dip it, completely submerge it, fill it up with mercury. That's a lot of mercury. And then you flip it upside down and you pull it out of the mercury bath, but you leave the end inside. You can do this with like a cup at home. Submerge a cup in like the bathtub or a sink, flip it upside down, and you pull it up, and what happens to the water that's in the cup? It also goes up. Same thing happens for mercury, but at some point, the amount of mercury, the mass of the mercury, is so much that it can't just keep rising up forever, because the thing that's keeping it up is the outside pressure on the surface of the water. So the pressure pushing down on the mercury in this case is what's forcing this mercury up. Once this mercury gets up to a height that's equal to the amount of pressure, it will no longer go up, and then you'll have a vacuum up at the top, or a near vacuum up at the top. And so the millimeter of mercury is based on how tall this column of mercury is. So the millimeter part is this 760 millimeters that we're looking at, the height of the mercury. This millimeters is a length measurement, which is normally what millimeters are. I just think usually when we talk about millimeters of mercury, we're not thinking of it as a length unit. And it's a length of a mercury column. We're great at spelling today. The reason that I think that this is fun and cool is because since it's millimeters, like the length unit of millimeters, we can convert it to inches by doing a millimeters to inches conversion, which I think is fun. It's not really that practical for all of us. I just think it's a cool trick. So atmospheric pressure at sea level will push a column of mercury to a height of about 760 millimeters. That's an important number. We'll see it again on this slide. Okay, some units of pressure are summarized here. We've got some important ones. 1 atmosphere, of course, very important. That's one that you should have memorized. 1 atmosphere of pressure at sea level, or at the ocean. We also have millimeters of mercury, mmHg. Millimeters of mercury are exactly equal to torr. mmHg, for all intents and purposes, is the same as torr. The numbers are always going to be the same. You don't have to memorize the pressure units, except for atmosphere. You should memorize atmosphere. But the rest of them, if you need them for unit conversions, you'll have them on the exam. Another one, a little bit more familiar to us, perhaps, is PSI. Typically, what we measure are tire pressure, or the pressure of a basketball, or our bike tires. We are typically measuring those in PSI, which is pounds per square inch. Pounds per means divide by square inch. So PSI. It's a unit of force over a unit of area. That's how a lot of our things are defined. Like our Pascal was newtons per meter squared. To do unit conversions, since we haven't touched unit conversions in a while, we would take any two things that are on this table. These are the air pressure at sea level, so these are all equal to each other. So if we want to convert 1.25 atmospheres to torr, the two things that we care about are what? What's one of our two units that we care about? Atmospheres. What's the other one that we care about for this problem? Torr. So we're going to take 1 atmosphere, we're going to take torr, we're going to set those equal to each other. 1 atmosphere equals 760 torr. We're starting with 1.25 atmospheres. That's the one that has the number with it. We need to make a conversion from 1 atmosphere equals 760 torr. It needs to have atmospheres on the bottom, which means that torr will have to be on the top. Divide both sides by 1 atmosphere. This is just a reminder of how we make conversion factors. 760 torr over 1 atmosphere. This works because the atmospheres cancels. And so what we're putting into our calculator is 1.25 atm times 760 torr. So we get 950 dot torr. If you take a lab on the Visalia campus in the chemistry building, they actually have mercury barometers on the wall. So for some of the labs where you have to measure pressure, you might get to read the pressure from a mercury barometer. Here we just use a digital device to do it for us. If we are converting from inches of mercury to millimeters of mercury, the two things that we care about are what? Inches mercury, 29.92 inches mercury, and millimeters mercury, 760 millimeters mercury. Starting with 30.15 INHG, we need to put the inches mercury on the bottom of our conversion factor. So 29.92 inches mercury. The 760 mmHg goes on the top. Inches mercury cancels. We're doing 30.15 times 760 divided by 29.92. We get out 765.8 mmHg. If we wanted to be cheeky with it, which I want to, we could also just convert the inches to millimeters. 1 inch is 2.54 centimeters, which is the same as 25.4 millimeters. So if we just multiply by 25.4, the inches part cancels and is replaced with millimeters. 30.15 times 25.4. We get 765.8 millimeters mercury. I'm just doing that to show you that you can do it that way. I don't expect you to do it that way. I think it's fun, so that's why I do it. Any questions about setting up for unit conversion problems? We get the numbers from a table. It's unit conversions like we've done before. If you're rusty on your unit conversions, Logan would love to go over unit conversions with you and feed you candy the whole time. Not like actually putting the candy in your mouth, but giving you candy that you can put in your mouth to enjoy while you're at his SI sessions. 1 to 3, Tuesday, Thursday. Okay, convert a pressure of that many mmHg into pounds per square inch. I'm giving you this one as an exercise, and we're going to leave up the relevant pressure values up there in the top right, and we'll scroll later. All right, we are converting mmHg into PSI, pounds per square inch. We have mmHg, 4394 millimeters mercury. We want to convert it into pounds per square inch, PSI. So we would need to extract from our table 14.7 psi, the pressure at sea level in psi, and also 760, bless you, millimeters mercury, that goes on the bottom. Millimeters mercury cancels. We're doing 4394 divided by 760 times 14.7. And we get a value of 84.98 ... PSI, and I would believe this rounds up to 85.0 PSI because of our 14.7 PSI conversion factor. For most of us, if you saw this, if you went to your tires in your car and you put a pressure gauge on and you saw 85 PSI, you should be shocked and alarmed. And you should immediately deflate your tires quite a bit, because typically the operating pressure for tires is like 30 or 40. 85 PSI would be reasonable for a road bike, because those typically go up to 100 PSI, depending on how firm of a ride you want. So that's unit conversions. We are also going to be doing a lot of equations, many equations. The first one, this is the first in a series of simple gas laws. Boyle's law. This is simple gas law, the first. Simple gas law senior, if you will. So the pressure of a gas sample depends, at least in part, on its volume. If temperature and amount of gas are constant, meaning you've got a closed container and it's staying at the same temperature, the pressure of a gas sample increases when you decrease volume. So pressure increases when volume decreases. The opposite is also true. So pressure increases when volume decreases, and if pressure will also decrease, the opposite, if volume increases. If we're filling up a bike tire, like with a bicycle pump, the way that bicycle pumps work, it's typically something like this. It's got a handle, it's got a big cylinder. You pull up on the handle, and that pulls air into the chamber. It's got a one-way valve on it, so when you push down, you're decreasing the volume in the chamber by adding a lot of pressure to it. That decreased volume forces the air through the tube into your bike tire. If you've ever pumped up a bike tire, especially a road bike tire with a not very good pump, you know that the longer that you pump, the harder it gets, because you're trying to force the air into the bike tire. As that pressure goes up, you have to apply more and more pressure on the bike pump handle before it will actually go into the bike tire. So by pushing down on the bike pump, your bike handle, you're decreasing the volume in the chamber. That increases the pressure in the chamber, forcing it into the bike tire. A lot of the hey, this is where it shows up in the real world, that's all just for fun to show you that this is somewhat relevant to stuff that we talk about. This is the more important slide, or one of the more important slides. So this relationship between volume and pressure is credited to Robert Boyle for its discovery. Boyle's law assumes constant temperature and a constant number of gas particles. We're always going to be able to assume that if we're using Boyle's law. So Boyle's law states that the volume of a gas and its pressure are inversely proportional. The way that we write this is with this fish-looking thing. The fish-looking thing means proportional to, as we saw earlier. And 1 over P is the inverse. So V is proportional to the inverse of P, or V is inversely proportional to P, would be another way that we'd write this. What the proportional means in math, also not necessarily relevant, that just means that it's equal to some constant times the thing that's on the other side. We don't know what the constant is. We're probably not even interested in finding out what the constant is. But I'm showing this to us because we can see how this turns into P1V1 equals P2V2. If we multiply both sides by P, you don't have to be able to do this derivation. I just think it's interesting. We get P times V equals K. What's K? It's a constant. Is it going to change? No, because it's a constant. Constants are constant. They don't change. So if we say, okay, well, K is constant, it's never going to change. If we increase P, that would change our constant unless volume decreases. And since the constant has to be constant, then V has to decrease. So we could say, all right, well, there's another state with a different pressure and volume. We'll call that state 2. We'll call the other one state 1. We don't really care what the constant is, so we'll get rid of it. And boom, we get P1V1 equals P2V2. That's how we move from the proportional to getting the equation. So Boyle's law, this, if you want something to memorize. There is a way that you don't have to memorize the simple gas laws, and I'll show us that. But that will come later in the lecture. For most of us, it's probably better to just have the gas laws, the simple gas laws memorized. The 1 here means state 1. The 2 means state 2. So 2 different instances, 2 different sets of conditions. Do you have any questions so far about Boyle's law? We're also going to talk about where it comes from. If we got rid of all the examples, if we got rid of all of the where it came from, we could knock this out in half a lecture probably. We're not doing that because that would be painful for you. So Boyle's law comes from this observation, and I really need to edit this slide. So this red bit that I'm coloring in is actually a different color. It just doesn't show up very well at all. So this red bit is air, or gas, rather. We'll call it gas. So Boyle discovered if you've got a little bit of gas in the end of a J tube and you pour mercury in, at some volume you're going to have a height of mercury. And remember, the height or the length of the mercury, that's where we get millimeters of mercury. So that's a pressure measurement, this height of the mercury. That's a pressure measurement. If you double the height of that pressure, double the height of the mercury column, the volume gets cut in half. If you triple the height of the mercury column, then the volume gets cut into a third. And so Boyle had some free time, I guess, and thought, oh, this is interesting, let's plot this data out. And he got something that looks like this. And that's not a very nice looking graph. But he didn't stop there. He just decided, well, let's graph it a different way. So if you graph pressure against volume, it's got that curved shape to it. If you're a math nerd, you know that looks like an inverse function. And sure enough, if you graph 1 over pressure against volume, you get a linear relationship. And we love linear relationships because they're really nice and simple. And so this is why we can use the 1 over pressure proportional to the volume. That's sort of where the idea comes from. So it's linear if pressure is inverted. If you inverted volume instead of pressure, that would also work. Kinetic molecular theory also explains Boyle's law. If the volume decreases, if we move the canister lid down, we're decreasing the volume. So we're forcing all the particles to be closer together. They're going to have more collisions. So moving particles into smaller volume increases collisions. Increasing collisions increases pressure. We're forcing them closer together, more collisions, more pressure, because the collisions cause the pressure. Let's see how we can use Boyle's law. A lot of the background, like where we get it from, is less important in terms of exam material compared to doing the calculations, which is why I'm kind of like breezing past a lot of the background and fun stuff. A sample of gas has an initial pressure of 2.44 atmospheres and an initial volume of 4.01 liters. Its pressure changes to 1.93 atmospheres. What is the new volume if temperature and amount of gas are kept constant? The last sentence, the if temperature and amount are kept constant, that's just so that you can't say, actually, you didn't say that temperature and amount are constant, so it could be anything. That's just covering our bases for that one weird scenario. So we have variables. For gas stuff, for gas problems, I recommend taking all of the information that you're given and writing it out on the side with labels to help us sort it out before we try to put it into a calculation. It's very important that we pair our data points correctly. So we've got, first up, a pressure, 2.44 atmospheres. We've got a volume, 4.01 liters. We've got another pressure, 1.93 atmospheres. We have pressure and volume and pressure, PVP. And we're looking for new volume, who dis? P, V, P, V. That should make us think Boyle's law. P1, V1 equals P2, V2. We currently just have them labeled as P and V. We don't have ones and twos. We got to put the ones and twos there. Arguably the hardest part, the most important part of doing most of these simple gas law problems, like with Boyle's law and other laws that we'll learn, the most important part is getting the variables paired up correctly. If you get the variables paired up correctly, the math is actually really quite easy. It's a tiny little bit of algebra. It's all multiplication and division. It's nothing too crazy. We've got one volume. Which of our two pressures does this volume go with? Does it go with our top pressure or our bottom pressure? It goes with our top pressure. Why does it go with our top pressure? We are told in the first sentence it's our initial pressure and our initial volume. Initial on both of those means those go together. I'm guessing that we're probably going to, most of us, call that our first state. Our first state is our initial state. We could also call it our second state. It doesn't matter what you call it, just as long as they're the same number. And that makes this other pressure our P2. How is our pressure changing? Our pressure is decreasing. If our pressure is decreasing, what do we expect to happen to our volume? We expect our volume to go up. So we are expecting volume go up. What we're finding is V2. We're expecting V2 to be bigger than V1. It can be helpful to think about the concept, like what do we expect to happen before we do it? That way, if we get something that we don't expect, we can look at it in a little bit more detail and maybe catch a mistake that we made. All right, using our Boyle's law, P1, V1 equals P2, V2. We need V2 by itself. That's what we're finding. To get V2 by itself, we have to move P2. Divide both sides by P2 to move P2 from the right to the left. Now V2 is P1, V1 over P2. You should always end up with one of the variables both on the top and the bottom, so those cancel out. The other variable will also be on the top. So flipping it left and right, V2 is P1, V1 over P2. We can plug in our numbers, our P1, 2.44 atmospheres, our V1, 4.01 liters, over 1.93 atmospheres. If we look at our units, we have atmospheres on the top and also on the bottom. Those will cancel out. We'll be left with liters. So our answer is going to have liters. 2.44 times 4.01 divided by 1.93. We're going to round this up to 5.07. So 5.07 liters, is that bigger than our initial volume? Yes, it is. That's what we expected. That's what we predicted. So it seems like all is well and good in our Boyle's law example. Any questions at all about rearranging our Boyle's law, labeling our variables, units? For this one, it didn't specify what units we need. On the exam, units will be specified. The units that you have to give will be specified. If I was nice when I made the exam, which I don't remember if I was, the units that you're given will be the same as the units that you get out when you use your Boyle's law or your other laws. So you don't have to do any conversions. That's not necessarily the case. Sometimes you might have to do unit conversions before or after you do your simple gas law. Charles' law relates volume and temperature. So this is our simple gas law number 2. Why does hot air rise? Hot air rises because heating a gas increases the volume if we're at constant pressure. If you're increasing the volume of the gas, the mass isn't changing, we're just spreading it out over a larger area, so the density decreases. Again, this is background stuff, so it's fun, but not really stuff that you need for the exam. Because the density decreases, it floats. Hot gas is less dense because it's more spread out, and so it naturally floats in air, in colder air. So the hot gas being less dense is going to rise. The cold air being more dense is going to fall. This is why if you've been in like a 2-story house, especially in the summer or the winter, the second floor is going to be considerably warmer than the first floor. The hot air all rises to the second floor, the cold air is going to settle to the first floor. You can also notice this probably in like a 1-story house. You would just have to go up and feel the air up at the top of the room and feel the air down close to the floor. Laying on the ground in the summer, sometimes nice because the cold air is down there. And this is how hot air balloons are able to stay up. It's just a giant balloon filled with slightly less dense air, and so it gets pushed up by buoyancy. Charles' law relates volume and temperature. Volume increases with temperature. If you plot volume on the y-axis and temperature on the x-axis in Kelvin, you get a straight line. And if you run this line all the way back, at 0 temperature, you should have 0 volume. At 0 Kelvin, volume is minimal. I'm saying it's minimal because it's not actually 0. We also haven't gotten to 0 Kelvin yet, but they've gotten really close. They've gotten to like, I think, nano or pico Kelvin. But this predicts that you would go back to 0 volume at negative 273 degrees Celsius, which is 0 Kelvin, and we call that absolute zero. This line is going to have some function that describes it. Do we remember what the formula, like the algebra formula for a line is? The general. Do we remember what that is? Yeah, it's y equals mx plus b. Do we remember what b is? B is the y-intercept. How high, where does the line hit the y-intercept? And if we're using units of Kelvin for our temperature, then it's going to hit at 0. So this is 0 when units are Kelvin. If we are not using units of Kelvin, if we're using temperature in degrees Celsius instead, our line would be somewhere like right there. There-ish. And our y-intercept would be here. Is that 0? No, that's not 0. And so we would end up with a number here for our b. This is important because if we don't have a b here, y could be volume, x could be temperature. We've got a linear relationship. It's a nice and easy relationship. And sure enough, that is what it is. J.A.C. Charles is credited with quantifying the relationship between volume and temperature. It assumes constant pressure, constant amount of gas. We can do the same thing with our proportional. Here they're directly proportional, meaning that they're both on the top. Directly, both on the top. This is for the Kelvin temperature. This V proportional to T, remember that trick we did earlier, where V equals some constant times the other thing? This looks a lot like the equation for a line without the y-intercept. If you have the y-intercept in there, you'd have to know what the y-intercept is. We don't know what the y-intercept is, but we know that k is a constant and it's always going to be the same thing. So that makes it nice and simple, and we can come up with, we can rearrange things to get Charles' law. So Charles' law is V1 over T1 equals V2 over T2. And again, the temperature has to be in what units? More people say it. Kelvin. The temperature has to be in Kelvin. So when the temperature of a gas sample, what's that say? In kelvins, is doubled, the volume doubles. Worth noting here, for the first time, temperatures must be expressed in what units? Kelvins, that's correct. Like I was talking about earlier, the equation of a line is this thing where the b-intercept, where b is the y-intercept. When using the what temperature scale? The Kelvin temperature scale, that's right. The y-intercept is 0, and that simplifies everything. It lets us use a simple equation instead of having to figure out what the heck is b. In kinetic molecular theory, I believe this is our 5th point, if the temperature of a gas sample is increased, the gas particles move faster. Hot gas is faster than cold gas. And that means a couple of things. One of the things is we're going to have more collisions. Because it's moving faster, it'll take less time for it to collide with stuff. The other thing is it's moving faster, and so when it collides, what does that mean? How does that change the collision? If you get hit by a car at 1 mile per hour versus a car at 50 miles per hour, what's the difference between those two things? Harder collision. One of them, you're probably fine, you're walking it off. That's the 1 mile per hour. The other one, 50 miles per hour, you're probably not walking. So hot gas is faster than cold gas. This means more collisions. More collisions means what? More pressure. But pressure is constant, so the volume has to increase. The other thing that it means is that there's more energy in the collisions. So every collision gives more force, which also would increase the pressure. Pressure is constant, though, so volume increases instead to keep pressure constant. But this is like the what's going on under the surface behind the scenes. You can play with Charles' law at home if you have a balloon and you've got access to hot and cold. So if you blow up a balloon at home, don't blow it up all the way or it might pop. If you put that balloon into ice water, if you put it in the freezer or into the fridge, it's going to decrease in size. The reason that it's going to decrease in size is because you're cooling down the gas that's inside. It's making fewer collisions with the walls of the balloon. It's making less forceful collisions with the walls of the balloon. The pressure outside has to equal the pressure inside, so the balloon is going to shrink. And then if you run it under warm or hot water, you'll see it grow. It'll get bigger. If you blew it up all the way to start with, when you run it under the warm or hot water, it might pop at this point. So if you're especially scared of balloons popping, maybe don't try this one. Okay, Charles' law example. Charles' law, V over T equals V over T, but number 2. A balloon is filled to a volume of 2.2 liters at a temperature of 22 Celsius. It's then heated to a temperature of 71 degrees Celsius. Find the new volume. So we've got a temperature, 22 Celsius. We've got a volume, 2.20 liters. And we've got another temperature, 71 degrees Celsius. Again, write out all the variables because you're going to have at least 3. For some other ones, we'll have 5 or more. We've got 1 volume and 2 temperatures. We need to know which of these 2 temperatures does our volume pair with. Does our volume pair with 22 or 71? Which one is the temperature for 2.2 liters? Is it the 71? Is it the 22? It's the top one, right? A balloon is filled to a volume of 2.20 liters at a temperature that's connecting them of 22 degrees Celsius. So we're going to call those T1 and V1, and then our other temperature gets the T2 label. We're finding V2. We need to rearrange Charles' law. We're going to move the T2 to the other side. So multiply T2 on both sides. We're going to flip it left and right. V2 equals T2 V1 over T1. What's our variable that changes? What's our condition that changes? Temperature, yes, our Celsius goes up, right? Our temperature goes up. What do we expect to happen to our volume? Is our volume going to go up or is our volume going to go down? Volume will go up. Volume's going to go up. I'm just going to write V instead of V2 because V2 is a set number. All right, so let's plug in our numbers. T2, 71. V1, 2.20 liters over T1, 22 degrees Celsius. Degrees Celsius cancels. 71 times 2.2 divided by 22. The number that we'd get out here is 7.1 liters. This is the wrong answer. If this was an exam, this would be one of the options. Why is this the wrong answer? The temperature has to be in kelvins. The temperature has to be in kelvins. For gases, the temperature always has to be in kelvins. If the temperature is not in kelvins, you will get the wrong answer every time. How do we convert to Kelvin from Celsius? It's our magic number that we add. 273.15. And for emphasis, we'll write a wrong. Wrong. I can't resist. Okay, our T1, our actual T1, the one that we can use in our problem, 295.15 Kelvin. Our actual T2, 344.15 Kelvin. V2 equals our T2, 344.15 Kelvin, times the same volume, 2.20 liters, over 295.15 Kelvin. It's very important that you make sure that you put the numbers in the correct spots. If you put them in the wrong spots, you'll get the wrong answer. So Kelvin cancels. We still end up with units of liters, but this time it's a smaller number. I also recommend for most of us that we do these conversions before we put it into the equation, because if you try to do them at the same time that you're putting it into the equation and you forget some parentheses, you get the wrong answer. You might get a crazy answer that I didn't predict, which could be helpful. That could be a sign to you. So we get 2.57 liters after we round. Our volume did increase. We went from 2.20 to 2.57. So we still got an increase in volume. That's what we predicted. Just not a crazy, like tripling our, more than tripling our volume. Questions? What did we learn from this example? The temperature needs to be in Kelvin. No matter how many times I say this, somebody is going to forget to put their temperature into Kelvin. Please remember to put your temperature into Kelvin. A gas in a cylinder with a movable piston has an initial volume, and it's heated from 25 degrees Celsius to 100 degrees Celsius. What's the final volume of the gas in milliliters? We started with milliliters. We're looking for milliliters, so we don't have to do any unit conversions. Take some time, try this one. I'm pleased to report that it looked like a lot of people were on the right track. Some of us were not. That's okay. This is the time and place to be wrong. It looked like everyone was doing the algebra correctly. It looked like a lot of the variables were identified correctly, and we love to see that. So we've got variables. We've got a volume that doesn't have a space before it. This is our initial volume. The cylinder is heated from 25 degrees Celsius to 100 degrees Celsius. So we've got volume, 45.8 ml. We've got temperature and temperature. They are 25 degrees Celsius and 100 degrees Celsius respectively, meaning in that order. We also have another volume. We are looking for this other volume, specifically in milliliters. That's what you'd get anyway. V1 goes with which of these two temperatures? Does it go with the 25 or the 100? It goes with the 25. It goes with the 25 because of this word from. From means that this is our initial state. From is where we started. To is where we're going. To is the final destination. So 25 degrees Celsius and 45.8 milliliters go together. That means our T1 is 25 degrees Celsius. Our 100 degrees Celsius then gets the label T2. What should we do right now? Convert to Kelvin. Because we have to. We might as well do it now. Get it over with. And now we're ready to rearrange and solve. We're looking for V2. We're going to multiply both sides by T2 like we did before. And we will get T2 V1 over T1. Since we already did our unit conversions, we can just go ahead and plug stuff in. 373.15 Kelvin on top, 45.8 milliliters also on top, 298 Kelvin on the bottom. The Kelvins cancel. What units do we have? We have units of milliliters. Are those the units that we want? Yes. Yes, those are the units that we want, so we don't have to do unit conversions. Sometimes you'll get different units than what you're asked for. Why somebody would do that to us, poor little us, to test us. So we get 57.3 milliliters. If you forgot to switch to Kelvin, you would have gotten 183.2 milliliters, which is way too high. If you liked Boyle's law, if you like Charles' law, I'm at the combination Boyle's-Charles law. We've got the combined gas law. So if you thought one was good, two's better. So we're putting together Boyle and Charles. Boyle's plus Charles. We're crisscrossing them, crazy style. Boyle's and Charles' law put together. Boyle's law, P1 V1 equals P2 V2. Charles' law, V1 over T1 equals V2 over T2. When we combine them, something magical happens. It's not really magical. We just bonk. Do we see just overlap? Isn't that cool? That's all it is. So now we've got this ugly mess. The amount of gas is constant. What else is notable about this? The amount of gas is constant. What else is important? The temperature is in kelvins. All right. So this is what a combined gas law problem looks like. We've got 5 variables now. We'll pick up here next class.